Okay, today's topic is the axis transformation, and we will first discuss when do we need it, and then we will talk about the formulation. Again, I'll start with the physical structure. Let's draw an actual structure and generate a wireframe model out of it. Again, I have a column, a beam, and another column. Let's put the foundation, footing. We have the footing, a single footing, that's the level of the soil. A simple frame, single span, single story, that's the height of the column or the floor level. And usually we have the column lines, column grid lines, and usually we know this length. Okay, now we said that while generating the structural model, this is usually what we do. We define the nodes at the story levels, so I have a node here, another node here, then in between these two nodes I have that beam element. I have a column, I want to model the footings as pin supports, another column here, and this is the usually floor to floor height, that's h, and this one is the center line to center line distance between these two columns. And we said that when you model, create a wireframe model like this, what the line that we draw actually represents the center line, the neutral axis of our actual beam elements. And here again, the columns are represented in their center lines from their neutral axis. So this is the model that we generate when we extend the wireframes. This is what we model. And if you compare these two models, of course, they are not exactly the same. We discuss the definition of the beam column intersections. Now let's see how we can improve the modeling of that beam. Now we say that the stiffness coefficients that we find, that we derive, is defined with respect to the neutral axis. Now the question is, if I move, this is still my beam element, but what will happen if I move the neutral axis by some distance in the downward direction? How would be the stiffness coefficients of this new element changes? If I can do that, then I would be modeling that beam as follows. And the nodes again defined at the top surface rather than the neutral axis or the middle of that beam. So the question is, how can we calculate the stiffness coefficients for a member who's defined the bending axis, whose bending axis is at the top? Okay, that's the question. So let's take a look at it. Now I have this, my original beam member, okay, and let's again show the depth. What I want to do is, that's D, so remember that we are modeling it this way, just from the center line. But what I want to do is to define the stiffness coefficients defined at the top surface. Okay, that's D. So I will move the bending axis, the distance in the upward direction. So what's the stiffness coefficients for this new configuration? That's the main question. So the way we do is, usually we will assume that I will have rigid members here. Okay, these two are connected with rigid members, And again, we will follow the same procedure. We will use the transformation approach. I know the stiffness coefficients for the degrees of freedoms at this ends, and with the help of this rigid member I will transfer them to the top surface, and the new stiffness coefficients will be the stiffness coefficients that I will be using in this model. Okay, so again let's use the same approach. I'll start with the displacements. I will relate the displacements, then I will relate the forces. So that's the top surface, okay? So I'm just defining some rigid members. I'm just assuming that as if we have rigid members here. That's our typical beam member. Okay, and we know the stiffness coefficients in D1, that's D2, D3, D4, D5, and D6. So this is our classical beam frame element, which I can calculate all the stiffness coefficients. But I want to transfer these displacements to the top node. So D1, let's call it M, D2M, D3M, D4M, D5M, and D6M. So the question is, what is the relationship between these two? Because with this relationship I can actually modify the stiffness coefficients. So let's transfer these displacements to the end of that rigid member. So due to the compatibility I should have the same displacements here. This is D6, D1, D2, and D3. And then I will need to relate these displacements with the displacements of the members at the top. So D1 will be equal to, it will first translate by the same amount, but remember that I have this rotation, and this rotation will create an additional translation in the direction of D1. So D1 would be equal to D1M plus the rotation D3M multiplied by the distance, which is equal to D. The vertical translations must be equal to each other, and the rotation, since it's a rigid member, must be equal to each other. Now let's take a look at this configuration. D4 will first move in the same amount with D4M, and again this rotation will increase the displacements at the bottom of that rigid member. So D4 will be equal to D4M plus D6M multiplied with the distance. The vertical translations are equal and the rotations are equal. So if I say that my U vector is equal to D1, D2, D6, and my UM vector is equal to D1M, D2M up to D6M, and if I want to write these relationships in matrix form, I have the following relationship. U is equal to transformation matrix, I will just say that that's the transpose of it, is equal to UM, and T transpose will be then equal to, I will just write these equations in matrix form. I got 1, 0, D, 0, 0, 0, 1, 0, they are all zeros. I have D here, 1, 0, and 1. and this part is all 0. So that's the transformation matrix, transpose of it. Now let's take a look at the forces. Remember that I don't have to do it because I know that it should be equal to T. Okay, but just to double check my formulation, I will do it. Again, let me draw the figure first. So I have these rigid members here. The rigid members here. I have my classical frame element. So the forces, the internal forces are F1, F2, F3, F4, F5, and F6. And here I have the forces at the transformed axis, F1M, F2M, F3M, okay, now let's transfer these forces to the ends of the rigid member. This is F1, F2, F3, F4, F5, and F6. Now let's take a look at these free body diagrams and relate the forces at the ends of the typical member and the forces at the end of the transformed member. So the forces in the X at this node, at this left-hand member should be equal to 0. This tells me that F1 M should be equal to F1. The forces in the vertical direction must be equal to 0. This tells me that F2M should be equal to F2. Then I'm taking moment with respect to that point. F3M will be equal to F3 plus F1 times D. Okay? So F3M is equal to F3 plus F1 times D. Now I go to the other node, repeat the same procedure. So F4M is equal to F4, F5M is equal to F5, F6M is equal to F6 plus F4 times D. Now if I write everything in matrix form, I have the following relationship. Fm is equal to the transformation matrix multiplied with the forces at the ends of the typical member. And if we write the transformation matrix, we have the following relationship. I got 1, 0, 0, 0, 0, 0. They are all zeros. Now here I have D, 0, 1, again 0. The end node, I have the following relationship, D, 0, and 1. This part is all 0. So if you compare again these two matrices, as expected, one of them is the transpose of the other. That's the relationship. Now we have the relationship that relates to displacements, a relationship that relates to forces. Now all I need to do is a relationship for the stiffness matrix. This time I will derive the stiffness matrix. I will start from the member and forces equation. F is equal to element stiffness matrix multiplied with the displacements at the end of that member plus the fix and force vector. Okay, so let's call this one equation star. I would like to call this one equation 1 and this one as equation 2. Okay, so inserting equation 1 into star, I have the following equation. F is equal to element stiffness matrix multiplied by T transpose multiplied by UM plus the fix and force vector, and let's call this new equation as equation double star. Now I will insert this equation into that. I'll rewrite these members, okay? Rewrite this one by using this equation. So I will just plug this into this equation, okay? So inserting equation double star into 2, I have the following relationship. So Fm is equal to T times K times T transpose multiplied by UM plus T times F fixed and force vector. And if you think about it, that's the relationship that gives us a new stiffness matrix, which we call it Km when you perform that transformation. That's the element stiffness matrix for a member whose bending axis is defined at the top surface. Okay, so that's the way you will obtain your new stiffness matrix. And if you think about it, you can just modify this procedure. And by modifying this procedure, if you want, you can move the axis of the columns towards right and left. You can move the axis of the beam to the bottom node. So you can actually play with it. The only thing that you need is that the distance. Today we will talk about the rigid diaphragm constraint. When do we use it and how can we formulate that? In reinforced concrete buildings, when we perform a 3D model, when we create a 3D model, we usually have a concrete deck and several columns connected to it. And of course, if you have beams, you have the beams connected to that diaphragm also. Okay, now if you think about the axial behavior of that slab, it has a certain thickness, usually 15 to 20 centimeters or even more, and it has a very large area. And usually when you compare the stiffness of this slab, the lateral stiffness of the structure versus the axial stiffness of the slab, there's a huge difference. This type of structures are very flexible in lateral deformation, but very rigid in axial deformations. So in order to simplify that type of structures, let me draw a plan view. We usually have columns at 4 corners, and sometimes we have beams connecting the columns. And we have the slab at the top. But when we want to model this by using the wireframe model, we will model the beams as follows. The columns, but the question is, how can I model the behavior of the slab? Because I don't want to model the slab, I just want to represent its behavior. Now, since we said that the lateral behavior of this type of moment frame structures is very flexible when compared to the axial deformation of this slab, we usually say that the slab is axially rigid. Which means that if this node translates by some delta amount, just forget about the rotation of the slab. I will see the same translations at these ends. Okay, so they move all the nodes, all the columns, the top of the columns move the same amount. And usually in reinforced concrete, we ignore the bending resistance of the slab. In case of a lateral load, we want to put all our capacities at the beams. So in this modeling approach, we need a definition that helps us to model a rigid, axially rigid slab. That's what we call a rigid diaphragm constraint. Now, in this type of definition, this is what we do. Assume that I have this slab, a rectangular slab. It doesn't matter, the shape doesn't matter actually. Let's say that that's the x direction, that's the y direction, and that's the z direction. And what I'm going to do is, at the centroid, I define a master node. Okay, the master node have the following in plane degrees of freedoms: ux m, uy m, and also a rotation in the z direction. Since the behavior of this rectangle is rigid, that's what we are assume, this can only perform a rigid translation in the x direction, and it can rotate. If you just think about it like that, this is the master node. It can translate in x and y direction, plus we will see a rigid body rotation in the z direction. So all the nodes that are on this deck will move rigidly. There will be no deformation. So let's take a simple node somewhere here. Let's take this node, and this node will have the following degrees of freedoms: uxi, uyi, and it also has this rotation zi. And the distance of this node to the master node is as follows. This distance is delta y, and that distance is delta x. Okay, and this is the figure related to the displacements. And let's draw the figure related to the forces. So I have this rectangular diaphragm. So at the centroid, I have the forces Fxm, Fym, and the moment Mzm. And let's show the forces at the same node. Fxi, Fyi, and Mzi. Okay. Now what I'm trying to do is this. Imagine that I have all these type of nodes here, and I'm trying to represent the degrees of freedoms of this node in terms of the master degrees of freedom. If I can write a relationship in between, okay, instead of writing all these degrees of freedom and writing the stiffness coefficients for all these degrees of freedom, I can just represent the behavior of this whole slab with 3 degrees of freedoms defined at the master node. This not only gives me a definition for a rigid diaphragm, but also helped me to reduce the number of degrees of freedom in my structural model. Okay, so our approach is nothing different than the rigid end offsets. I want to relate the displacements of a typical node with the master displacements, get the transformation matrix, and then do the calculations to obtain the new stiffness matrix. Now, what is my relationship between the displacements? So uxi will be equal to, I should have the same translation with the master node, uxm, and remember that there is a rotation, okay, and because of this rotation, this point will move in the opposite direction. So I have minus theta z m multiplied by delta y. Okay, that's the relationship between the uxm and the uxi. Let's write the same relationship with uyi. They will translate the same amount, and again, because of this rotation, I will see some additional translation. So I have plus theta z m multiplied by delta x. Since this is a rigid rectangle, theta z I will be equal to theta z m. So these are my relationship between the degrees of freedoms, between the degrees of freedom of a typical node and the master node. Let's take a look at the forces. So sum of forces in the x direction must be equal to 0. So this tells me that Fxm must be equal to Fxi. Sum of forces in the y must be equal to 0. So if I take moment with respect to the centroid, I got mzm equal to mzi minus delta y times fxi plus delta x times fyi. And these are the relationship between the forces at the typical node and the forces at the master node. If we write everything in matrix form, so on one side I have uxi, uyI, theta zi equal to my transformation matrix multiplied by uxm, uym, theta zm. And in the transformation matrix, I got 1 here, 0 minus delta y. That's my first constraint equation. 0, 1, delta x, and 0, 0, 1. Let's write the relationship in the forces in matrix form. So we got fxm, fym, and mzm on one side, a transformation matrix, and I have fxi, fyi, and mzi. Now the relationship is as follows. I got 1, 0, 0, 0, 1, 0, minus delta y, delta x, and y. So as you see, if I call this transformation matrix as T, the matrix that transforms the displacements is actually the transpose of the transformation matrix. And since we have that, we can write the following, and we will do it for every node. Okay, so ui is equal to T transpose multiplied by the displacements or at the master node. If you have any loading applied to a particular degrees of freedom, you can transfer it to the master node with the following transformation: T multiplied by Fy. So that's the way we transform the unbalanced forces. And the stiffness matrix written with respect to the master node is equal to T times K multiplied by T transpose. And you repeat it for every node, and then whatever you find, you assemble it to the stiffness of the master node. And these are the transformation matrices. So I'll just say these transformation equations are for a single nodes in plane degrees of freedom. So with the help of these transformations, we can define an axially rigid slab by defining its behavior with only 3 degrees of freedoms. Okay, This not only help us just to create a wireframe model for a 3D structure composed of beams and members, beams and columns. And here we define a rigid diaphragm constraint. And also it helps us to reduce the number of degrees of freedom, because I may have many, it doesn't matter how many nodes I have on the stack. At the end of the day, the in-plane behavior will only be described by these 3 degrees of freedoms.